Hey team, I'm Maddie. Welcome to Science Side Up. And today we're going to talk about how we know how old the solar system is. Hallelujah, it's Uraniu-men. So you may have noticed my lack of regular blackboard and some changes. I'm working on setting up a more permanent recording space in my garage. So I tore down everything in here before realizing that I had a lot more work to do than I'd initially thought. So we're gonna do this video with this pad of paper and markers before I can get everything together for the next video. Hopefully we can use the new studio. Okay, so let's get into what we're gonna talk about today. So specifically, today we're going to talk about uranium-lead dating and how we use that to date the solar system. And so it's important that you know that uranium is naturally occurring in 3 isotopes, uranium-238, 236, and 235. So maybe as a quick refresher on what an isotope is. So nuclear science land, we're going to write uranium like this. So 92. That's the number of protons in a uranium nucleus. U is its atomic signal, and then 238. So uranium-238 has a total of 238 neutrons in for neutron plus proton. Oh my god. This is so awkward. Okay, so let's try to not flip the camera again. All right. So uranium-238 has 238 neutrons plus protons. Because it is uranium, the number of protons doesn't change. So this is always 92, right? So if we had uranium-235, that's 92, uranium-235, that means 235 neutrons plus protons, right? You can see that. So there's 92 protons in uranium-235 as well. So the difference between uranium-235 and uranium-238 is 3 neutrons, right? Uranium-238 has 3 more neutrons than uranium-235. If you were to go into the ground and dig up some uranium, right? You go to your uranium mine, then you would find that 99% of the uranium you dug up was uranium-238, and that other 1% is about 0.7 or 70% uranium-235, and then the rest is uranium-236. So uranium-238, overwhelmingly the most abundant, and then uranium-235 is the second most abundant, but it only makes up, I say second most abundant, and that's true, but it's only making up 0.7% of all uranium that you would go find in your uranium mine. Uranium-238 will eventually radioactively decay to lead-206. 206, that's the total number of protons and neutrons in the nucleus. And uranium-235 will eventually radioactively decay to lead-207. If I have something that's really, really old that has uranium and lead in it, right, we can figure out how old that thing is based off of how much uranium is there and how much lead is there. Okay, so what we have 2 clocks, right? Uranium-238 to lead-206, uranium-235 to lead-207, and we want to use these tools to measure how old the solar system is. Okay, so what should we go measure? What object is going to tell us how old the solar system is? Okay, so bear with me for a second, because this is some really specific science words. We want to go find calcium aluminum inclusions in carbonaceous chondrite meteorites. So how do I know that that's the thing that we should be dating? That's a great question. And this all gets down to solar system formation. So when the solar system forms, It starts off as a disk of gas that's orbiting what's called a protostar. And all of this is really, really, really hot. So we're keeping everything that now makes up the planets, right, that's now in rocks in our iron core, right? This is all a gas. It's so hot that even the iron is in a gaseous state. And as the solar system starts to form, though that gas in that disk starts to precipitate out and solidify. So we can know, right? We know at what temperature and what pressure different elements and different compounds are going to precipitate out. Okay, so if you take a look at this graph, so this has temperature on the bottom and then I think total percentage of the solar system on the y-axis. But notice at the hottest temperature, so on the farthest to your right on the graph, at the hottest temperatures, what can condense out and become a solid is really heavy in calcium and aluminum. That Ca is calcium and Al is aluminum. So calcium aluminum inclusions. So these are going to be crystals, things that were the very first things to precipitate out of that protoplanetary disk. So that means that that's the very first part of our solar system that formed. And then these get included into a really specific type of meteorite that's called a carbonaceous chondrite for geology reasons. So now we have what we want to date, right, the calcium aluminum inclusions, and we have our tool, the uranium lead dating. But I said calcium aluminum inclusions. Why would that have any uranium? Excellent question. So CAIs are mostly calcium and aluminum, but they can also have magnesium and titanium in them, amongst other elements. But the titanium is actually what's important. Okay, so pretend with me for a minute. We're going to imagine that we are, oh my gosh, building a rock, okay, or we're building a crystal. That is this box. This is the rock we're building. And this, we have a round hole, okay? So this is a really simple way of illustrating. We need the right type of element that's going to fit into this hole. And whether or not it will fit, chemically speaking, is dependent upon the valence of the atom. Basically, titanium is the right thing to fit into this hole, right? I said that titanium is something that we can have. So let's make pink be titanium. And titanium is much more abundant than uranium. So almost all of the time, when we're building this crystal, titanium is going to go in there. But it turns out uranium should probably be green. Uranium is the same shape, right? It has the same valence. So that means that when we're building a rock, we can substitute in uranium for titanium every once in a while. And more importantly, lead is the wrong shape, right? So where I can include uranium into this crystal structure, I can't include lead. And that's important because that tells us when we look at these CAIs now, right, now there is some lead, right? Well, how did that lead get there? Because it definitely wasn't put there when we built the thing, right? So the only possible way the lead could have gotten into that round hole is if it started as uranium and then radioactively decayed into lead. So this tells us that any lead we find in these calcium aluminum inclusions had to come from radioactive decay. With a little bit of algebra, which I'll actually work it out and post that as a separate video, but we can get to the following equation. Bam! Okay, so this says that the concentration of lead-206 that I have now relative to the concentration of lead-207 that I have now is equal to the concentration of uranium-238 that I have now over the concentration of uranium-235 that I have now times just E, that special number, times to the negative decay constant for uranium-238 times time minus 1 divided by same thing, but for the decay constant of uranium-235. So what's awesome is that we can measure both of these things in the meteorite. We can measure both of those things in the meteorite. And then those decay constants are things that we can know. For uranium-235, uranium-235, that's about 700 million years, is the half-life, not the decay constant. So that just different units, same idea. So the half-life for uranium-235 is about 700 million years, and then the half-life for uranium-238 is like 4.5 billion years. So what that means is that we know everything in this equation, right? We either already know it or we can measure it, except for the time. So the time just tells us how long has passed. And so when we solve for time, right, that's going to give us the age of the solar system. So what we want to do is find as many of those calcium aluminum inclusions as we possibly can, date all of them, compare all of the times that we get, right, and use that to get at our number. And our current number for the age of the solar system is 4.567 billion years old. And now you know how we figured that out. So if you thought this was cool, I first learned this from a class at MIT called 12002, because MIT measures everything in numbers. 12002 is physics and chemistry of the terrestrial planets. So what's really cool about MIT is almost all of their classes, almost all the class material is available free online to anybody at OpenCourseWare. So in the description, there is a link to the OpenCourseWare page for that class, and that has some resources if you're more interested in reading up on some of this. So it'll tell you, like, it's got lecture notes, it has some of the homeworks, and then it also has, in the syllabus, it'll tell you, like, the textbook, which is a really great resource if this is something you're interested in. Okay, team, that's all I've got for you today. I hope you liked this video. Be sure to like and subscribe. Let you know what you thought in the comments. If there's a topic you'd like me to cover, let me know. And hopefully next time I see you, we will be in my designated studio. Okay, until next time.